So we talk about we started to talk about SVM. I will walk kind of wrap up this today, and let's just go back a little bit. Just review a little bit. We'll talk about logistic regression as a classification. So if you think of you have some features, let's say I have two classes, just two classes, that I want to separate these two classes. So as a classification problem, you can think of like maybe I can like project all of this data. So this is a data in high dimensional. So this is each of this data can be think of a vector. If I can project to this axis, let's say this axis as W, and then I kind of like, if I project this way along this line here, after my projection, of course I add a bias here also. So basically, if this is an X here, I project this, I have Wx or W transpose X plus B, something like that. Then I go for a logistic function. So logistic function is something like a sigmoid function like that. So then I would say like what how do I the sigmoid function like that. So then the output can be regarded as some kind of probability or some kind of belief. So believe that it belongs to this group. So basically you see like on this side here is pretty big, right? So like this guy here is probably the probability to belong in, maybe this I call it class, maybe this is cat class, is not cat class. So belong to that cat class is pretty high. Yeah.
The coefficient you found formula is 6 or?
This is sigmoid, yeah. This is sigmoid. That's only for my handwriting. So it's a sigmoid. So it's like something like 1 over exponential, something like that, like something this kind of stuff, minus something. So maybe minus x. So then we also mentioned, okay, this is logistic regression, right? So how can we kind of gauge whether this classifier is good or not? Will be based on, last time we talked about, we will use a cross entropy loss, right? So do you still remember the cross entropy loss? Actually, can you explain what is cross entropy loss? It would be nice if you were able to explain it, because this is something you will see all the time, right? People will talk about the cross entropy loss. You may even come up this question in your interview. Let me ask you, what's cross entropy loss?
Isn't there another name for it?
Not really. So it's a cross entropy, just cross entropy. So I don't think there's another name for that. But if you remember, like the cross entropy is something like have this form like this. And essentially, you can think of this as it's a KL divergence plus some constant. So essentially, what you're measuring is like, as we discussed last time, is really the distance between the ground truth distribution. In this case, basically, we know, for example, this point here, for sure it's a cat, then I can say it has a non-cat probability is equal to 0, and then the cat probability is equal to 1. Right? And I want to measure this distribution with another distribution. Is I say for this particular point here, let's say xi, I estimate from my classifier, I estimated that the probability is equal to pi. So, and therefore, like I may have something like cat probability is pi, and then of course no cat probability in this case would be 1 minus pi. So then the cross entropy in this case will be what? Will be equal to log by the way, I actually didn't elaborate this example last time. I only talked about for multi-class, but so you can think of these two classes like multi, right? One class, two class. So if I elaborate, that would be log cat class, right? P cat class, and then like the Q cat class. Q is basically the ground truth for the cat class, plus Q log cat times log P log cat. For this particular sample. So then here I assume that that sample is actually really a cat, right? So therefore Q cat is just equal to 1, right? And Q log cat here is just equal to 0. So therefore, like, actually that for this particular sample, the cross entropy is just equal to log P cat. Maybe I didn't emphasize last time also, like, for your cross entropy, you're measuring one sample. Like each time I'm doing here is just measuring one sample, right? So if I have like n training samples, the total loss will be like sum over all these. So therefore, like I should sum over kind of like, let's say I equal to 1 to n. Let's say I have n samples there, and sorry, this index is actually referring to some things. Maybe I don't use I here. Let me use small n's here, not to confuse you guys. So this I here is like it's basically like different classes here. It's like different classes. So this n here is different sample. So and I will have Qn. Maybe I put it here just to make the difference. Plus 1 minus Qn. So this will be the cross entropy loss for two classes classifier with n samples. So of course, like for each sample, like this Qn can be either 1 or 0, depends on like whether your sample is actually a cat or not a cat. So any question for this one? This is the cross entropy here. So one thing I want to emphasize is that, like, yes? Yes?
Just wanted to emphasize the fact that is there any particular difference between Q and P, or these are just probabilities?
That's different. That's okay. Q is the ground truth. Q is the ground truth. So that's what really happened. Is the Q is the ground truth, and P is the estimate probability from the classifier. So, and in this example, like Pn will be like the estimated probability of the n sample by the classifier to think that whether it's a cat or not.
Okay.
Yeah.
Thanks.
Yeah. So, okay. So, any other question? Yeah.
What is the ground truth?
A ground truth will be, because this is the training data, right? Here, like, we are looking into training first. So you know for sure, this is supervised learning, so you know each sample was whether it's a cat or not. Yeah, so, yeah. So,
the truth is like
so for example, like on this side, all of them are cat. So therefore, if let me label it. For example, like this is 1, 2, 3, 4, 5, 6, 7, 8, like that. Then like for sample like Q5, for example, like this should be equal to 1. I mean, for this guy here is equal to 1, and Q1 is equal to 0. Yeah, because this side is not a cat. Yeah. So any other questions? Yeah, before you guys questions, actually what I like to emphasize is that like if you look at the loss here, we take each of these samples into account, like each of the training sample contribute to the loss function here, right? Because we sum over this and all of them have some values here. And one thing pretty different for like support vector machine, as you can see, only the support vector is like has contribution to the loss actually. So if you remember, I'm not going to restart my derivation, but if you remember, maybe I can cross out something. Maybe I cross out, let's see if I can cross out. Maybe I cross out some cross entropy here. So if I'm thinking about support vector machine, the goal of support vector machine again is I want to find this projection, right? I want to find this projection W. But this time I try to, for example, if I fix this projection W, then I want to see what's the gap between the two samples, the maximum gap. Of course, in this case, I want to make sure that none of the samples will fall into this margin here. I don't know whether I should call it gap or margin. I cannot. So the maximum margin is allowed here. It will depend on the direction, right? For example, in this direction, my margin is like this white here. If I change a little bit, it looks like if my W, for example, if I swap to this direction, I may get a little bit better result. Let's see. For example, if I go here, it looks to be a little bit wider. And for support vector machine, the goal is to make this as wide as possible. And in this case, you see that like actually only the sample touching the boundary will have some contribution to the loss. For the rest, actually, this doesn't affect the loss at all. And I will skip the derivation, but last time, but I will just write down the conclusion we have last time. Is like, if you look at the length of this gap, the length of this gap is just equal to 2 over W. And so yeah, the length of this gap is equal to 2 over W. We want to maximize that. But of course, there's some constraint here because we want to make sure that like length of the sample will be fall between this gap here, and to get outside the gap, we have the condition that like on this side, basically, okay, if you remember, like this line here, we have something like equation W transpose X plus B is equal to 1. This is a W transpose X plus B equal to -1. And for convenience, I use the label cat and non-cat, but let's say cat is the Y will set to 1. This is the expected outcome for the classifier. So the label will be 1, and the other side I will set -1. So it will be, if I use this notation, it's more convenient. Then if I do this, then I can basically I can combine these two conditions into just one line. This basically will require that like for all samples like yi, maybe I write like this, yi W transpose xi minus b has to be bigger or equal to 1. So that's where we ended last time. So it's like we show that like SVM is essentially trying to solve this problem here. Any questions? It can be questions from last time actually if you. That should be plus, I think. It's okay. Like I am. I use my, actually, of course, it's not important. Let's use plus. I use minus in the slide. So if you put plus, then it's just like I have b equal to minus b. It's not important. But so then of course this is trying to maximize this gap, but I can also like change this objective function. Maximizing this will be the same as minimizing w, right? And I can even say like minimizing w squared, the second norm of that. That is actually even easier. That basically is like w transpose w. And for convenience, I can even put a 1/2 there. So then I can change my equation to, let's say, minimizing w transpose w over 2, something like that. Now, so how to solve this? Anyone know how to solve this? Do you guys take any courses in optimization or like some? Really? But you have a math minor. What?
Partial derivatives.
Yes, but be careful. We have a constraint here. If you just take partial derivative of this guy here, you're basically ignoring this constraint here.
Didn't offer optimization courses.
Oh, really? Wait. Calculus, something should say something about this. I don't know. When I did my undergrad, like calculus, something did talk about this. I don't know about OU. Really?
I think there was
What's that?
$5,000.
Well, maybe.
Yes?
Well, maybe something similar to, say, scientific computing methods in which we just put a value and see the answer, and then if the answer does not, and make a variation in that answer, if the input variation increases or maximizes the output, then we decrease the input. If it increases the input, then we decrease the output in a vice versa way, so that we can step by step reach at the optimized level.
Yeah, good try, but here, like, it can be easier than that. Like in some cases, maybe we don't have any way to do that. Like then, we can do what you're talking about. Essentially, something like gradient descent, right? So if you blindly put numbers, it would be like impossible. But maybe you can do a gradient descent. Like I just try to start with some point there. I take the gradient of this guy. This is maybe I call it this objective function. Call it something. I call it what O. Then I can compute this partial derivative O, or like the gradient of O with respect to W. Then I want to minimize, right? Then I would just go along the negative gradient of that. So I can set like W equal to W minus this multiplied by some epsilon, something. Then I'll go downhill. Then I need to verify whether this constraint is satisfied every time. If it's satisfied, then I will just try to continue to do that. So it can be some kind of like gradient descent, but this won't be, in this case, easier than that, first of all. Easier in the sense like computational wise, like this will be like much more complicated, or like will be computational intensive. And secondly, like if you randomly try to find a number whether this constraint is going to be satisfied, actually even these steps can be very complicated. Like you need to first start with looking for W actually satisfy all these constraints. So you have, let's say, 100 or 1,000 data points. You need to make sure find a W that satisfy all these constraints. It can be very difficult to start with.
Yeah.
So a kind of like I would call it a canonical way to do this. Maybe if I say it, then you guys kind of maybe remember that. You may have seen that somewhere before. So maybe I keep this part. So do you guys heard of the Lagrange multiplier? Did it come to your memory? So when you have a constraint, kind of like basically this is a classic way to solve like constraint optimization. Is that you try to absorb the constraint into your objective function. After absorbing that, then it's like a unconstrained optimization problem. Then as Robbie said, like I can just take a gradient. And so in this case, like what I can do is I can consider this, minimize W transpose W over 2, and then I write like this. Let's see, minus alpha I y I W transpose x I plus b minus 1. Okay, and this is minimized over W, and let me try to maximize over alpha, and I want alpha I to be bigger than or equal to 0. So now let's see why I can do that. Like let's see like why I can do this. So I am claiming that this optimization problem is kind of equivalent. These two are actually equivalent. So why is that? If you look at just this inner part, the inner optimization here. So I'm trying to optimize over alpha and alpha I. So this is so-called the Lagrange multiplier, something like redundant. So I am trying to optimize over alpha I is bigger than or equal to 0 here. Now, I can have like either this constraint, one of these constraints is satisfied or not satisfied, right? Let's say if all my constraints are satisfied, if all of them are satisfied, then all of these numbers will be bigger than or equal to 0, right? Then I try to maximize this thing over all the alpha I here, because this is all positive. Then, and also I optimize over the range that alpha I has to be bigger than or equal to 0. Then alpha I will be just equal to 0, right? In this case, if alpha I equal to alpha I will be just equal to 0, and this part will be basically gone. This part is just gone. And I will just get back like originally minimize this thing here. Okay, but if I have one of the constraints is not satisfied, let's say if I have the first sample is not satisfied, I have y1 basically W transpose x1 plus b is less than 1. If this is not satisfied, then this will be negative, right? So then in that case, I'm trying to optimize this part, trying to maximize that over all the alpha I, right? So because alpha I is unbounded, right? I can set alpha I to be anything as long as this is bigger than or equal to 0. So I can pick alpha 1 equal to infinity, basically, right? So if alpha 1 is infinity, then this whole thing will be just equal to this plus infinity, right? So then what I have like after this will be like this thing will be equal to infinity. So in summary, just this part basically will be equal to W transpose W over 2 if all constraints satisfy. Or equal to infinity otherwise. And of course, then you have the outer optimization here is trying to minimize, right? So then, of course, I won't pick this otherwise, right? Because in this case, this will be like infinity. I'm trying to minimize this function. So therefore, I will try to always, in this case here, that is basically like I will look for cases that all constraints is satisfied. So is that clear? So why these two optimization is identical? So, and then then next thing, okay, it doesn't look like this do anything to solve this problem, right? No, at least not yet, right? So, but so it's a good start. At least we have solved the constraint, and now, of course, we still have a constraint alpha I bigger than equal to 0, but it's easier to solve. So it looks like we just translate the problem in another form in a sense, but it looks like it could be simpler. So then what next is, how about, this is like a little bit cheating. It's like, instead of solving this problem, let's swap these two optimization. So let's consider minimizing first, and then maximize. So is that okay? Does it make sense? Yes, it does not make sense, actually. It does not always make sense. So, I mean, like, but that's the thing. Like, this is actually, sometimes these two will have the same solution. And we are hoping that these two have the same solution. If these two have a same solution, then will be like, this will become easier to solve. Because if you look at that, once we swap this optimization here, so we have this guy is just a unconstrained optimization over W, right? Then we actually can solve this part. Then after we solve this part, what we have remaining is actually maximize over this guy, maximize some objective function. That is a function in terms of alpha. So at the beginning, we have this function is like some function in terms of W, right? Now after this kind of like transform here, eventually I will have some other optimization problem that basically optimize over some function, maybe I call it G alpha, that with respect to alpha. And actually this is in optimization, like it's known as some dual problem. So so this oops, the original known as the primal problem, and this known as the dual problem. And so in general, the solution for this guy will be bigger than this guy, actually. But if you think of like, if they turns out that if they are identical, then what happens is like, I'm not going to prove it, but I'll at least give an argument that like at least one condition has to be satisfied. The condition is like all of these guys here has to be equal to 0. Or like for the optimum alpha and W, so let's say I have the optimum alpha I star and optimum W star, I will have this part like alpha I star yi W transpose, I should put a star here, x I plus b minus 1. All this for all I will be equal to 0. Oh, sorry. For all I, this will be equal to 0. So why is that? Because if you think of that, like it turns out these two are really identical. Remember, like what I'm trying to solve this one here is really just trying to minimize these things here, right? And now if after I optimize this guy here, I have this part is identical to this guy. I have W transpose W over 2. Let's say the optimum will be like W star transpose W star over 2. If this 2 has to be the same, then this means this part will be equal to 0, right? So all of this will be equal to 0. And this has a name for that, as long as the complementary slackless condition. And also, like, besides this condition, of course, from this guy here, since I'm trying to minimize this over unconstrained optimization over W, if I call this whole thing, I'm sorry, it's a little bit hard to read now, as a function LW alpha, let's say, then I should have the gradient LW alpha should be equal to 0. So I have this condition, I have this condition, and I should also have condition, let's say alpha I is bigger than equal to 0. Let's see what else. And also I have the original optimization condition that basically this y I w transpose x I plus b should be bigger than equal to 1. So I will have all these four conditions has to be satisfied. Then these two kind of optimization problem will give me identical solution. I'm not going to give a proof for that, but this is known as the KKT condition actually. There's a story for that. This is I think it's a Kawush. I forgot the name, Kawush. Kuntaka, I think it's when I was in undergrad, it's called Kuntaka condition. And then later on, someone realized that Kawush have a master thesis. I worked on that earlier than whatever published. So then later on, people put his name back, and then now it's like KKT condition. So it's like it's a very nice master thesis, and it's not very hard to prove, but as you can see, it's very general, right? Because it basically solves any kind of constraint optimization problem, basically. So now let's continue trying to solve this. So as I mentioned, okay, we are going to change from this trying to solve this problem into trying to solve this instead. That basically swap this minimization and maximization. And then this is because I'm trying to minimize W over this guy here, like this is unconstrained, I can just set the gradient equal to 0. And then let's try to do this. So basically this guy, let's try to compute the gradient over W. I should get something like W, right? If I take a gradient of this guy, I should get something like W, and then minus alpha I y I x I. I guess it's just like that. Like this other part is basically constant. So this should be just equal to 0. So therefore I get basically W is just equal to this, equal to I alpha I y I x I. Then I can substitute this back into this one here. Oh, actually, by the way, because B is also a parameter here, right? So actually here, even though I only put W here, I also put B, because B is the I can also optimize the B, will be basically the offset here, right? W is just where I'm pointing, but I can set where should be the middle part there. So you seems to have a question for that. Okay, so then I can also take gradient over B. So B. So for B, what do I get? B only this. I have something here, so it be basically get alpha I y I should be equal to 0. Do you agree with that? Kind of like this way. And this thing is, you expand that this thing is directly multiplied to this guy, right? So if I take derivative with B, then only this left. So therefore just this is equal to 0. Now then use these two equations and put back to this one here. Maybe I try to because I keep using this, maybe I try to copy down here. So let's I have this again and this again. Then I substitute back. Then W will, this W transpose W will be something like sum over I, sum over J, alpha I, alpha J, yi, yj, and then I have a x I transpose xj, something like that. I have a 1/2 also, and then this I have alpha I here, yi, W transpose is basically sum over j, alpha j, yj, xj, and I have a transpose here, and I have a xi somewhere here. This is from this guy here, xi, plus b minus 1. So it looks pretty ugly, but trust me, like this have I, j, right? So this summation can pull back here. So I have alpha I, alpha j, have xi transpose xj. Basically, this term and this term is the same. So I just cancel it out, just have 1/2 that remaining minus 1/2 ij, alpha I, alpha j, yi, yj, xi transpose xj. And then let's see. And then I have this multiplied by b, right? But this guy, we already see that this is equal to 0, so therefore this term is gone. So the only term I left is this multiplied by minus 1. So therefore it's just a plus sum over alpha I. So therefore, like, okay, the optimization problem kind of the dual optimization become like this. I will try to solve this instead. So it turns out that, like, I'm not going into detail of this. This is quite easy to solve. It's actually quite a bit easier to solve than the primal solution. The way to solve that is like you will start with like some alpha. Basically, you pick some alpha that come randomly. Then you can go back to look at this KKT condition. I'm so sorry. Like maybe I can emphasize this. Like, these are the KKT conditions. Let's see where is the I have this also. This is a complementary slackless. Or this I already used that. I don't need that. So I have these conditions here. So I can I can check, like, let's put in some alpha. Then we will need to look at, like, whether the conditions are satisfied. If it's satisfied, then we'll find another pair of alphas. And then, like, if they are not satisfied, then if just for that particular alpha. So then what we're going to do is, like, we'll fix all the rest of the alphas. We'll just change 2 alpha at a time. If we just change 2 alpha at a time, this may be a little bit hard to see. But if you write it down, this is really a quadratic function, quadratic problem. And then you can just, because it's a quadratic problem, you have a closed form solution. So you basically pick 2 alpha, you get the closed form solution for that. You take another pair of alpha, then you get the closed form. I'm continue to iterate like this. So this is called known as this sequential. I I forgot what's M stand for. Let's see. M is stand for, oh yeah, just minimum. So it's just sequential minimal optimization. So this is by John Platt. So if you are really interested, you can just go look for his paper. So it's like one of the standard way to solve like the support vector machine problem. So I let's see. I have a couple remarks here besides solving this problem. So first of all, once you have the optimum alpha, so let's say I have the optimum alpha, so I have the optimum W. So my W will be just represented by this guy, right? It's just represented to alpha I star multiplied yi and xi. Now here I'm going to test whether something is a class A or class B, or like whether it's a cat or not cat. So in this case, I will just use this alpha. So I should go back to try to look at like W star multiplied by some incoming x. And then I press B. I want to check whether this is like bigger than 0 or less than 0, right? To decide whether it's like belong to, is a cat or not a cat, right? Now, if you look at that, the alpha, the W is just this way. So then I look at that, what is this? This is a sum over I, alpha I star, yi, xi, x transpose. So it's like this guy plus B, something like that. And one thing I want you guys to pay attention is that for alpha I, most of the alpha I is actually equal to 0, because earlier we said that like, we need to satisfy this complementary slack left solution condition. This is actually the condition that if you look at this again, like I probably didn't emphasize enough for this condition. If you look at this condition again, what is this condition? When this is satisfied, when this is satisfied, I mean this part is equal to 0. What does that mean? Let me circle it more clearly. What does that mean for this part equal to 0?
So it means it's not lying on the margin?
Oh, more than that. It's not just not lying on the margin. Actually, it's exactly lying on the boundary. Right? On this side would be like bigger than equal to 1. Let's say like actually this both sides will be bigger than equal to 1, but if I ignore this y here, this will be like bigger than equal to 1, x transpose w transpose x plus b is bigger than equal to 1. This will be w transpose x plus b is less than equal to 1. If I have this equal to 0, it's exactly lying on this boundary. This is actually the support vector. So the samples there are the support vectors. Now maybe I should then ask them, how about those is not equal to 0? So if those not equal to 0 will be outside the boundary. Outside the boundary, since this is not equal to 0, then the complementary slack left condition saying that like then the alpha has to be equal to 0, eh? So that means that like for each point here, you have actually for each of the training points, training data there, training sample there, you have a corresponding alpha, and only the alpha lies on the boundary. That basically support vector will have alpha is non-zero. For the rest, alpha will be all equal to 0. So therefore, if you look at again like this here, when you do testing, you do an inner product of your x with some of the incoming x with some of your sample, training sample, but not all the samples, only the samples that have non-zero alpha, right? And basically, you're only doing inner product of x with the support vectors. So that's also, at least when the computation, a decade or two ago, like it's more expensive. Then like this is a very attractive feature, right? Because you can have like very few support vector really, right? You can have like 10,000, like 20,000 samples, but ultimately you may have like only a few support vectors. So computational wise, it's like it's cheap basically. Another remark, I guess I probably forgot to mention, is like if you look at the optimization problem itself to begin with, it's actually interesting. We have this after Lagrange multiplier, we are basically trying to minimize this W something, and with this constraint here, right? And this guy here is pretty much, if you remember, it's like a regularization, like in Lasso, right? If you remember, like when we talk about linear regression, we can again try to minimize some loss there. It can be just like some your desired output. Maybe I write desired output as yi minus your actual output, let's say yi again, and then square. So this is maybe the square error. So you want to minimize the sum square error, but we mentioned that like this alone can easily overfit, right? Then one way to reduce overfitting is like we can add a regularizer. Basically, we can include the typically, for example, like the sum of all the weights there of the model. And interesting is support vector machine is kind of self-regularized in that regard if you look at that, right? Because just presenting the problem itself, like you already have this term trying to minimize. You're already trying to minimize the weight of your of the model itself. What else? Any question? So one more thing maybe I should mention is like, so since you, I know this is pretty tense. Honestly, I spent some time preparing that. Like if I didn't prepare that, probably I cannot explain this, because 1 week later I will forget also. So therefore I'm taping this, like for my convenience, I can come back to listen to this. So
Dr. Chang, I
yes.
have a question.
Yes.
How do you come up with a reasonable value for alpha?
Oh yeah, actually I missed that. A short answer, go to this paper. So it's eventually trying to solve this problem, and it turns out this problem is like can be quite efficiently solved this way. So you will fix some alpha in this way. You just like initialize with some alphas, and then you pick two alphas at a time. You cannot just pick one alpha, because like this alpha not completely unrelated, because we have a constraint like this here. So like alpha actually are related somehow, but we can vary two alphas at one time. Then we pick two alphas, and then we will try to optimize just two alphas. Then if you only consider the two alphas and fix everything else, it turns out this problem will be just a quadratic problem. So we'll have a closed form solution. So it's therefore very quick. Each step is very quick. Then you just keep repeating that. So but there's some minor detail like I don't honestly remember. So I will just direct you to this paper like by John Platt. This is like work in late 90s, like near 2000. Like he was with Microsoft at that time. I don't know whether he still is. Yeah. Yes. Did I kind of answer your question? I guess not completely.
I'll go look at the paper.
Yes. So
One more thing, Dr. Chang.
Yes.
Can you please emphasize the fact that alpha isosteric and W isosteric, when given the optimal value, equal to 1 when we plug in those values in the above equation. So why is it so that for optimal values the equation equals to 1?
It's not equation equal to 1. Actually, it's like this guy here. I just saying that like this has to be satisfied. This multiplied with this alpha I has to be equal to 0. Like this one here. Remember, like from this optimization problem here, this is actually the Palmer problem is essentially the same as this guy here, right? It's just equal to this guy here, but with this constraint here, right? But then we say like these two optimization problem does not necessary to be identical. But when it's identical, then this part, this tail part better equal to 0, right? Otherwise, there's no way they will be identical, right? So this tail part is just this complementary slackless condition. So we want this, all this Lagrange multiplier with the constraint. This is actually general. Whenever you have something like that, the Lagrange multiplier multiply with that corresponding constraint has to be equal to 0, and it's called the complementary slackless condition. So what I just said is just it's not this has to be equal to 1, but I'm saying that like if this is not equal to 1, this will be equal to 0, right? Because this is satisfied, right? So then for those alpha will be just equal to 0. We don't need to care about that. Did I answer your question also?
Yeah, to a certain extent.
Yeah.
I shall surely look the paper as well.
Oh, okay. That part won't be related to the paper. You better ask me now, because he take this as background knowledge. He show more this like for the Lagrange multiplier and stuff like that. KKT conditions. If you want to know more about KKT condition, you can look for. But I'm not sure. Like I didn't really look at the original paper, but Karush or something. You may try to search for that. I don't know a good reference for that actually, because I typically just use that for the condition. I just argue my way through because I didn't actually try to prove that, and it looks like all these conditions, if it doesn't satisfy, it doesn't make sense. For example, like this complementary slackless condition, this better to be 0, right? If this part is not equal to 0, like how can this part is equal to that original part here? Yes. So, but yeah. Actually, I actually for that part, honestly, I think you can just look for Wikipedia because KKT is quite famous. Yeah.
Sure.
Yeah. Okay. I guess then the final thing, final thing I like to mention is, you see that like when you actually use to test this, you only involve like inner product of like your training sample and your input, and then this comes up with another idea known as the kernel trick. I think Robbie mentioned that, like, but in another context. So the kernel trick is like actually even in I guess one of our class like earlier, like we not exactly doing a kernel trick, but try to have the same flavor. It's like I have sample here. It's maybe the original sample have a dimension, I don't know, the vector sample maybe dimension k. I can somehow like project these samples into a higher dimension, maybe like how can I make it bigger than k? Maybe big K. Oh, that's bad. Maybe a big K. This is a small k here. So essentially, like I can project this into a higher dimension. So basically, like this is originally x. Then I have a find function become find x, and this is a dimension k. Big K. This is dimension small k, and big K can be quite a bit bigger than small k. And then this will allow you to have like this allow you to have a more complex model, that have able to separate regions that originally is not separable. I guess I'm not sure. Like I forgot to prepare that, but like some of this classic example, for example, if you think of this, you have two classes here. If I just try to linear separate this, it's not separable, right? But let's say if I have this is x1, x2 is two of this dimension here. Now I extend this to give it a third dimension. Let's say x3 is equal to x1 squared plus x2 squared. Then if I look at that now, originally it's just k is small k is just equal to 2, x1, x2, right? Now I have k is equal to 3 map into x1, x2, and this is x1 squared for x2 squared. Now suddenly this becomes separable, right? Apparently, I only use the third feature that essentially just the radius. I can separate these two data sets, right? So, and this is essentially the same idea. If we project into a high dimensions, anything is originally is not separable, it becomes separable. But the problem is like this mapping can be very expensive to do, and you may be looking at a really high dimension, but luckily because we only look at inner product, actually we don't even need to do this projection to do this projection to this high dimension. We can just define something like whenever I have k, let's say xy, that hopefully will be equal to this phi x, phi y, the inner product between them. So of course, I actually I don't know what is this essentially most of the time, but I would just assume that like I am able to I will have some function to replace this. So a classic example is like I can have a kernel, say it's like a Gaussian kernel will be just something like exponential x minus y over similar, something like that, right? And this will be correspond to a very complicated file, probably like a file we cannot written down, but this essentially project to a very high dimensional space. So then essentially like instead of like doing this inner product things, we'll just replace all this inner product with this kernel function, and then like the optimization is essentially we can do the same thing as before, and this is the kernel trick, and that's also why support vector machine was actually it's still powerful, but like it's not as yeah.
Hello, Dr. Sam.
Yes.
So if we have to increase the dimensionality, I mean, does this not introduce the cost of dimensionality? I mean, if we increase into a higher feature space, I would expect that this will introduce this cost of dimensionality.
Yes, it's true, but it's exactly similar to the neural network. Where we put more layers, more parameters, we will have like cost of dimension, something like that. Like we will have easily have overfitting, but we also introduce a co-regularization, right? We put in dropout and stuff like that in neural networks. And here is actually the same thing because, as I mentioned here, the optimization problem for like support vector machine itself is like kind of self-regularized. You have this actually included like in the model already, so therefore it ends up is working quite well, and that's why like when you have like reasonable amount of data, like you work really well actually. Of course, you have many data, then maybe neural network will beat this. Yeah. And let's see what is there anything I want to. Oh, and of course I'll just mention. Where is that? I'm trying to look for my. Oh yes.
Sir,
Yes.
I wanted to ask that how we decide that from small k to capital K, how much to increase, like from 2 to 4 or 8, how do we decide that?
This is a very good question. Actually, I can't skip very quickly. Typically, what happens is we don't know. Actually, I guess a short answer is you just use a Gaussian kernel. Be careful, we don't actually compute this fine here. We don't need to know what's this fine here. So essentially, it's like when you have this x in this small k dimension, we actually just replace all the inner product by this guy instead. And yes. And actually, I missed out something. Maybe I will just mention this also. It's like, so how do you know the kernel is valid? Because it doesn't necessarily the kernel is valid. In the sense that kernel is supposed to be valid. It's like if you make up a kernel, then maybe you cannot write it down, but theoretically it should be equal to some inner product between some phi x and phi y, right? Where this phi x and this phi is basically the mapping to this higher dimension. And first of all, you can observe that because it's an inner product, right? So therefore, this kernel function should be symmetric because this should be equal to phi y transpose phi x, right? This should be the same. So the kernel has to be symmetric. And you can also easily verify that if I consider x just any m vectors here, if I consider any m vectors here, and let me build this time be careful, this I call it a kernel matrix, maybe I write like this, kernel matrix, let's say m by m kernel matrix. This is a matrix of m by m, where the ij element is equal to the inner product of actually just equal to k x I and xj. So the ij also okay. It's like here the ij element is equal to that. So meaning that my matrix, maybe I just erase it here. My matrix is, so therefore my k is something like that. This kernel matrix is like k x1 x1 k x1 x2 and so on and so forth, right, up to k xm xn. So if the kernel is a valid kernel, then basically for any x1 up to xm, this matrix has to be positive definite. So meaning that if I multiply by a vector z and multiply by z transpose, this has to be bigger than or equal to 0. So it's very hard to prove. Actually, I don't have a proof on my slide, but you can verify that at least if your kernel is valid, so in the sense that your kernel is actually equal to some inner product between phi x and phi y, or phi in this case phi xi and phi transpose xi and phi xj. Then this kernel matrix for any x1 up to xm, this has to be positive definite. But this has a am I making it clear? I'm sorry. I think maybe I say it again. If my kernel is valid, so in the sense that my kernel function is valid, then it can be written as an inner product of some high dimensional mapping, right? Then I construct any kernel matrix in this sense. Then this matrix will be positive definite. That basically I multiply by any vector C transpose on this side and C here. This will be bigger than or equal to 0. And this is actually very easy to prove. the hard thing to prove is by Mercer, that basically showing that like for any vectors, if I pull out any vectors and construct a kernel matrix, if that kernel matrix is also positive definite, then that kernel will be a valid kernel. That one I really if that one will involve lots of math. That one I'm not going to that. But like if you just want to show the kernel matrix is positive definite, it's actually easy to show. I put it on my slide, but I guess I will skip that now here. So let's see if I guess I still have a little bit something I want to say, but I'm not sure I will. Maybe quickly if I see I can. So one thing I want to mention is like for the original problem here, maybe I just mention the setup and then I will actually elaborate more next time. It's like, so how about if you have data point, like this is a pretty ideal situation, right? This is kind of separable. So how about if I have data points actually not separable? Maybe I have some points here, like it's apparently there's no way I can separate them. Then in that case, I need to convert my problem. Like in that case, all these constraints must not be satisfied, right? Then I need to convert this problem to a kind of a soft margin problem that I allow that sometimes, for example, I have a sample here is kind of off from this margin here, and then the easiest thing will be like instead of trying to force this is bigger than equal to 1, I can modify the constraint to something like that, right? Maximum yi. Maybe I leave a minus sign here. See, kind of makes sense, right? So basically, if this constraint is satisfied, then this will be negative. Then my loss will be just equal to 0. And if this constraint is not satisfied, then this will be positive, right? So then we'll have a positive loss there. So then basically I can kind of add this. Instead of trying to minimize this, I can minimize this plus some constant multiplied by this guy here. So okay, I guess I will just stop here. Then maybe I'll really wrap this up next time. Then we'll start talking about neural networks. So if you guys have any questions, just yeah.
Should we read something or do something
See that again?
Should we read or watch something about this mathematical concept?
I think it's up to you. It's good to know, especially I think this Lagrange multiplier, I guess is common knowledge. Like for the support. What?
I remember.
Yeah. This is a very much. It's good to, for example, KKT condition is actually very good to know. That's also why I spend a little bit time talking about that, because it's something like you encounter all the time, and actually it's very useful. And the kernel check actually is very useful as well. Of course, it's not clear like how we are going to combine this to new Lagrange, but this may come back. So if you kind of like, but that's basically like the kernel tree is nothing, right? It's just like whenever you have some, actually it's not just like in support vector machine, it's like used everywhere. You can have like kernel, kernel linear regression, kernel whatever. Like you can kernel anything, as long as your classifier or like basically if you have process that you're going to process only depends on inner product, right? So essentially, I will replace all the inner product by a kernel function, and that the kernel function, I'm somehow like I am able to typically say I can able to train some of the parameters even after this modification. Then I can use this kernel trick, right? So so therefore, like, this is only one example, but I think these two concepts is very, very useful because they appear everywhere, like Lagrange multiplier and the kernel trick, basically. So, anyway, I will come back to talk a little bit more. Like, maybe you guys will have more questions next time.